and share my screen again. Turns out I forgot to plug in my computer. And let me get the chat up here just in case somebody wants to talk to me. There we go. All right. Move this on screen. Okay, so Lewis acid, Lewis base, electrophile, nucleophile. That's the key phrase here. Okay, so if that is true, we can use that same nucleophile electrophile argument for Bronsted-Lowry, right? But we need to start thinking about them as our conjugate acid, conjugate base, because that'll tell us whether or not the reaction has a where's my stylus? Oh, there. Okay, so if we're doing it as a Lewis acid base, then, I'm sorry, if we're doing it as a Bronsted-Lowry base, we have our acid, which looks like HA. And then we have our base, which is B with a lone pair on it, so we can see them. And we have some kind of equilibrium where the proton is transferred. So you end up with base with the acid transferred to it. And we end up with our acid with our those electrons. So these electrons are being used to make the new bond with the hydrogen, sorry. These electrons are staying with the acid to give us our new thing. And so if this is our acid, this is our conjugate acid. And if this is our base, this is our conjugate base, okay? So our acid turns into our base, conjugate base. Our base turns into our conjugate acid, okay? So why do we care that something is transferred, the hydrogen's transferred? Well, it's written as an equilibrium here, meaning you can transfer back and forth, right? So the direction to which the reaction goes for starting materials or products, or the acids versus the conjugate acid, depends on the acid strength. So acid strength is about how far it's shifted this way or that way. Acid strength is how much do you want to give away this hydrogen. If you want to give away that hydrogen and not get it back, you're a strong acid. If you want to give that hydrogen away and want it back half the time, you're a weaker acid because you want to pull that back, okay? So when we think about this, we have to think about stuff like, okay, if it's not going to do it equally, or it's not going to do it all the way, we now have to think about it as, if I'm willing to give my proton away, and let's just use water right here. And when I'm doing that, these electrons come over to this hydrogen, these electrons stay on here, and we're left with plus and a lone pair plus A with an electrons with a negative charge, not a positive charge, right here. How likely is it to have your acid go 100% over with water to give you the hydronium ion? If it's a very strong acid like HCl, it's going to do it almost 100%. But in something else like acetic acid, it's not going to do it 100%. So measuring the difference between how much it's donated or how little it's donated gives us an idea of whether it's a strong acid or a weak acid. Okay. So do we see how the propensity or the tendency for the acid to donate its hydrogen makes it a stronger acid or a weaker acid? The more it wants to give it away, the stronger acid is. Okay, so what does that mean? Well, we actually have to measure that, okay? It's not something you can predict. So if you take your equation and say, okay, I have a Thank you. Let's minimize that. Okay. We take our acid, react it with water right here, and put our equilibrium signs in here to give us our conjugate base here with our negative charge on it and our hydronium ion. We actually can't predict where this is. We have to measure it. So by measuring that, we can figure out what the equilibrium of this reaction is. And so whenever we talk about an equilibrium, we have a constant where it's going to go one way for a while and then the other way, and then eventually it kind of settles in the middle. Okay. And so to figure out where that equilibrium is, we have to think about what is the concentration of the products over the concentration of the starting materials. Materials. Okay. Why? Well, because if it's 1-to-1, then your equilibrium is somewhere in the middle, right? It's just they went halfway to start, the materials halfway to the product. But if it's swayed one way or another, that equilibrium constant gets very big or very small. Okay. So in the case of our acid-base reaction up here, we actually have to do the concentration of hydronium ion, because that's a product, the concentration of whatever the conjugate base is, divided by the concentration of water initially and the concentration of the acid initially. Okay, so when we do this with things that transfer with the hydronium ion, when we do things with water, we can actually cancel out the concentration of water because there's so much of it. And we end up with what we call an acidity constant. The acidity constant is equal to the concentration of water times the equilibrium constant, which is equal to hydronium ion over concentration of the conjugate base over the concentration of the initial acid. Okay, and this gives us an equilibrium constant for the acid. Takes out the water, and so we have our acidity constant right here. Okay, so if we think about it, if it has more of the products than the acid here, your number on the top is very, very big. Your number on the bottom is very, very small. Okay, so what we end up doing is we actually, because they're very big numbers, we end up taking the natural log of, the base 10 log of it, and we actually have what we call the pKa. pKa. Okay. So let's define that. Okay. In the case of our pKa, we've just taken the log of our Ka. Our Ka is that acidity constant. Okay. So in the case of strong acids, we typically see them to have a pKa of less than 1. Okay, so HCl, HBr, that kind of stuff. So like HCl has a pKa of -7. Okay, acetic acid, no, we'll get there. Then if we have a range from 1 to 3, we call that a moderately strong acid. That's things like phosphoric acid. It has a pKa of 2.1. Okay. Then we get into our weak acids like acetic acid. Acetic acid, CH3, which is our first carboxylic acid that we're going to talk about. It has a pKa of 4 to 5, 4.25, not 4 through 5, depending on what it's a substance. But then we get into things that are weaker than that. So acetic acid is what we consider our weak acid. Our first organic acid is what we call acetic acid or carboxylic acids. Then we get into weaker organic acids, and it turns out things like phenol and alcohols. Phenols right here, which is an OH on a benzene ring, has a pK of around 10. Okay, and then everything above that is 15, the pK of 15. Turns out water has a pK of 15, 14.8. Alcohols have a pK of 15 or 16. So we're looking at alcohol and water as weakly acidic, very weak acids. Okay, so it's all defined on that pKa scale. Okay, so when we talk about the general scale here, we want to talk about our acids in the context of the pKa. So we have our HCl, which is our strong acid, and then we have acetic acid, and then water just above 15, alcohols just above 15. Okay. So if the smaller the number is, the stronger the acid, the larger the number, the weaker the acid, right? So when we get to stuff like hydrogen, that has a pK of 35. And if we get to the hydrogen carbon bond on an sp3 hybridized carbon, you're like, hey, that's not acidic at all. It's not a polar bond. Well, it's very, very, very weakly acidic because it has a pK of 50. But if you have something strong enough, it can pull that hydrogen off. So think about it that way. This is a very weak bond, but if you have something that can pull that off, it will. Okay, so if this is increasing acid strength, let's now look at our conjugate base. Okay, so if this was a very strong acid, it wanted to get rid of that hydrogen so fast, it would give it to anything, that its conjugate base must be very stable. Its conjugate base must be very weak. Okay, so that's the interesting thing. A very strong acid has a very weak conjugate base. So they're diametrically opposed, right? So what if we had something like, okay, we took that proton off methane. It was a very weak acid. What kind of base is it?
Strong.
It's a very strong base. It wants to accept hydrogen so badly that it will strip them off anything below the list. Okay, so this is so strong, it'll take protons off of anything below it on that list of acidity. Think of it that way. So very strong acid makes very weak base. Very weak base makes very strong acid. Okay, questions on that? So there are a few of these values you should memorize. I'll actually put a table online. It's things like acetic acid, phenol, water, and methanol. These are things that we're going to use a lot. We're going to use those pKa's. It's a table about 10, okay? I'm going to put all the strong acids together, like HBr and everything. Those are all less than 0. But those are the ones you really should memorize. And we're going to talk about acidity as a function of hybridization. Those ones you'll need to know as well. Okay, so we'll talk about those as we go. Now, do not confuse pKa with pH. Do not confuse pKa with pH. We do not have to have water in our system to have a pK, because look, we can't have water in our system if we have this base, because it's going to take all the protons off everything below it, including water, hydrogen, alcohols. It's going to remove those hydrogens. So we can't have the water in our compound. So when we talk about pH, it describes it in water. So if we had our pH is equal to our log of hydronium ion. Remember, we took hydronium ion out. Hydronium ion is in the conjugate acid and base are on the top of that acidity constant, and the acid is on the bottom, which means the pKa is the log of the acidity constant. Remember, acidity constant has the concentration of the initial acid, the conjugate base, and the conjugate acid in it, not just the concentration of hydronium ion. So they're not the same. And we can see this and make sure we understand this by looking at acetic acid. If we react acetic acid in the presence of water, so in this case, acetic acid is acting as the acid, and the water is acting as the base. It's going to give us a hydronium ion here. And therefore, we can calculate the pH of this solution. We have a hydronium ion. We have the log, the negative log of the hydronium ion. So that means the pH is equal to 2.4, because that's the log of the concentration of hydronium ion. But the pKa, like I showed you on the last table, is actually 4.8. So if we're measuring the acidity of acetic acid in water, we can measure pH. If we're measuring the acidity of acetic acid not in water, we use the pKa. Most of the time, we'll be using pKa in this thing because it's not the same. Okay, questions for the difference between pKa and the pH? We use pH almost exclusively in Gen Chem. We're going to use pKa almost exclusively in organic chemistry. So, all right. So what does this have to do with equilibrium? Okay. So if something is a strong acid reacting with a strong base, they're both strong, the equilibrium is probably going to lie to the product side, right? But now let's say we don't have, it's not that strong, and maybe the base isn't that strong. We see we have a big variety of different acids and base strengths. So how do we figure out whether it lies to the products or the reactants, okay? So let's start with one we're gonna learn, and I'm just gonna start with this one right here. This is acetylene, and the pKa of the hydrogen on acetylene is 25. Okay, so it's not like methane, which is 50. It's not like acetic acid, which is 5. It's 25. And we have it in the presence of a very strong base. We have this amide right here. And we're trying to decide which way this reaction is going to go. Okay, now we could go and actually calculate out what our pKb or our base strength would be, or we can just compare the acid strengths. It's like, well, but I only have one acid and one base here. We got to finish the reaction, right? We have to transfer that proton. Sorry. When we transfer that proton, we now have a conjugate base. And when we transfer that proton, we have our conjugate acid. Okay, so all we have to do is compare the pKa of our acid to the pKa of our conjugate acid, and that'll tell us which way the reaction's going. So in this case here, this ammonia, NH3, I drew it kind of funny here to show you the proton was transferred to those electrons. The pKa is 38. Okay, which one's stronger, 25 or 38? 25 is stronger. The lower the number is stronger. So which way is the equilibrium going to lie? To the stronger acid or the weaker acid? To the weaker acid. So which way is it going? It's going to go that way. So you don't even need to know the base strength. All you need to know is the pKa of the acid and the conjugate acid, and you can tell which way the equilibrium is going to go. Okay, so if we did a different reaction and you came up with a pKa of 22 on this side and a pKa of 3 on this side, it's going to go to the weaker acid, the higher number in pKa. All right, we got 5 minutes. right? Okay, let's continue on with this. All right, so how do we know which is which? How do we know which is going to be good, which is going to be bad? So we just have to go through and get our balanced or get our equation set up so that we have our acid and base identified on the reactant side. And then we have the conjugate acid and the conjugate base defined on our product side. And we compare the pKa of the acid to the conjugate acid. And that will tell you which direction the reaction is going to go, whether the products are favored, going to the weaker acid on the product side, or whether the starting materials are favored, going to the weaker acid on the reactant side. So sometimes reactions won't even go because there's not enough acidity on one side or the other, and it's already the weaker acid, and there's no reaction. Okay. So I'm going to save this next one for Wednesday. Wait, it is Monday. Monday. So we're going to talk about the 4 factors that affect acidity in organic compounds. Okay, the 4 things that'll change the pKa. Okay, so you can read ahead if you want, but that will be. All right, any questions online here? I'm going to go ahead and stop sharing. And meeting for everybody.